Hello and welcome to Sorting and Storing Data, Stacks, Queues, and Heaps. You lucky student you get to learn about different ways to store data. We'll start with a stack. To help with visualization of this abstract idea, first think of your favorite stackable object. It could be books, it could be pogs, it could even be lunch trays. Have you got it? Good. I'm going to ignore your preference and use pictures of kittens instead. So we have our cute pictures of kittens. Aww. Oh, to put them into a stack, we're going to use stacksAdd method, which is called push. Don't ask me why it's called push. Just accept and obey. Now, we have a stack of 7 cute, fluffy little kitty pictures. But how are we going to get them back? We're going to use stacksRemove method, which is called pop. I don't know why. We aren't using Lego bricks, so there's no reason for them to be stuck together. But again, accept and obey. So, pop once, and again, and you get the idea. To further explain, stack structure is what is known as an LIFO. No, not lost information from Oregon. Last in, first out. The last object added to the stack is the first object we take off of it. Some useful methods for the stack class are the peek method, empty method, and size method. The peek method allows the user to look at the object on the top of the stack, since pop removes the item from the list, meaning that you've changed the stack forever. Peek allows you to see it without altering the stack. Next is the Boolean method empty. This is to check whether or not the stack is empty. Duh. And lastly, a size method will return the number of objects in your stack. To import the stack class, use this import. For more info on the stack class, go to this hyperlink, or just Google search stack plus Java. Next on our wonderful educational lesson on data structures is the queue. Now you might say, sir, that is pronounced K, like it is Spanish or something, not Q. But believe me, as a reformed K'er, I urge you not to make an embarrassing social mistake and advise you to call it Q instead. Now then, queues are exactly what they sound like, a queue or ticket line. People get into line to get movie or concert tickets, or to pay for their groceries, ATM, any number of situations, there's lines involved. Our lucky stick figures are waiting in line to get movie tickets to see the next Star Wars movie. Yes, I know I'm a nerd. Anyway, as people get into line, the people that arrive after them get attached to the back of the line, and as the people buy their tickets and exit the line, they start from the front. This structure is an FIFO. I don't have a cutesy misunderstanding acronym joke for this one, besides, I used that one already. FIFO is first in, first out. Like it's the high school teacher that signs up to chaperone the prom, but they sign up so that they're there for the first hour, and that's the hour where there's no kids. Anyways, I digress. The first people added to our line, the ones that showed up 12 hours ago for the movie, are the first ones to get their tickets and finally get to sit in the theater after 12 hours of standing. Java has the queue class preset in its java.util package, and has the offer method for adding to the queue, the peek, just like the stack class, for looking at what's on top, the poll, yes, like it's an election, or remove for removal of items from the queue, that's from the head since it's first in, first out, as well as a size method to determine the number of objects in the queue. You can visit this link for more info, or just Google search Q plus Java for more methods. Next are heaps, which surprisingly are not unordered, unstructured piles of crap, but an extremely specialized type of binary tree. This is one of the most complex types of structures, so I apologize in advance for the lack of jokes that you've either liked or rolled your eyes at every time I've tried to spice up the video. A heap is a binary tree with 2 rules. Rule number 1, the tree must be complete. Complete doesn't mean that it's found its true love, or able to do sports and AP classes while volunteering at the nursing home, but that the missing values of the tree or the spaces vacant for the addition of children are on the bottom and to the far right. Rule number 2. each parent node is less than the two child nodes. Now, take a look at our tree. If you'll notice, and you should, since it's not like you have anything else better to do at the moment, you'll see that this diagram satisfies the two rules. Each node is less than its two children, and the vacant spaces are to the far and bottom right. Here, it's also important to point out that for use later, these nodes are indexed starting with the top as 1 and going down to each level, labeling them from left to right. Since I cannot find a preset Java class, I will now explain how adding or removing data is implemented. Sorry. When you add a node to the tree, you always add so that the empty side is to the far right, satisfying our rule number 1. Now, as you can see in our diagram, the child is less than the parent, violating our other rule. As thinking human beings, we can see that the added node should go here. If you didn't see that, you need to go cry in the corner. Immediately. Anyways, we make the entire data structure reheap up, switching the parent and the child and continuing to do so until the added node is in its proper place. When removing a node from a heap, you always remove the root node. But, we've got a hole in our tree. Right there. Never fear, the solution to our predicament can always be solved by the always valiant Final Leaf. Okay, so it's not your regular superhero, but it's working on it. Our Final Leaf takes the place of the root node. But, again, all is not well in Heap Town. Final Leaf has violated rule number 2. We see the return of reheap, except this time in the form of reheap down. This will switch our replacement node with the smallest of its two children until it reaches its final spot. At the end of its descent back to the depths of the heap will be restructured and all will be well in the heap again. From our wonderful structure of the data heap, we get the priority queue. It is what you would expect. The data is stored in order. The preset class imported with java.util puts objects in their order such that 1 is in front of 2 and A is in front of B. But if you want to start comparing apples to oranges, apples are better, then you might want to consider writing your own priority queue. There are many different ways to implement a priority queue, most obvious coming to mind being the array list and linked list structures. But they are ultimately limited by the fact that you have to reorder the entire list when adding or removing objects, which can be pretty nasty. It's kind of like using a brick to hit a nail when you have a hammer you could use. So what's the hammer? Heaps are the hammer. A data heap already orders data by significance, whereas for linked lists and array lists, you would have to write the code for addition and removal of the data. The only pitfall of working with heaps is that you need to tailor your thinking so that the most important objects are lower on the list, kind of like a top 10 heap, 1 being the most important and 10 being least important. Well, thank you for sitting around through my explanations. I hope the pictures didn't confuse you. If you didn't understand them, it's okay. It's my humor.